Okay, I think we'll get started. So today we're going to start the first of several lectures on a really important technique called titrations. This will help us understand the reaction when we don't have exactly stoichiometric amounts. So we had practiced that last time. Now this will push us into a more general situation. And then just from its utilitarian perspective, titrations are really important in chemistry, particularly analytical chemistry, where we're trying to figure out how much of something is in a solution. And so the basic setup is that we have a burette, which is able to deliver a known amount of volume. So we can control the burette and deliver exactly a known amount of volume. We deliver what's called the titrant to the solution containing the analytes. The analyte is what we're looking for, and the titrant is some kind of standard that we're using. Oftentimes, we need to add an indicator to help us determine when the reaction is over. So in order to do a titration, there's a couple of characteristic things that we need to have. The reaction needs to be fast, so we can't have a sluggish reaction because we don't want to just dump some of our titrant in and then we have to wait for a while for the reaction to complete. We want the reaction to go very fast. We also want the reaction to be complete, or as complete as possible. So we want like a good acid-base reaction that will go, or some kind of oxidation reduction reaction that will really go towards products. Then most often, although sometimes the titrant or the analyte can be its own indicator, some kind of color change or some other thing we can measure happens when we get right to the stoichiometric amount. But otherwise, we need to have some kind of indicator in the solution. Now, what is the indicator trying to indicate? It's trying to indicate right when we have passed from the analyte being the excess reagent and the titrant being the limiting reagent to right where they're equal, so there's no excess reagent, to the other side where the titrant is the excess reagent and the analyte is the limiting reagent. So we transition through that, what's called equivalence point. That's when exactly the same stoichiometric amounts of titrant and analyte are in solution. That's called the equivalence point. What we see physically is not the equivalence point, but we see the end point. So this is when some kind of change happens. In a very typical Gen Chem experiment, you would be reacting hydrochloric acid with sodium hydroxide. So we'll do that as an example over here. And we put in some phenolphthalein indicator, and that's clear when it's acidic, and then it turns pink when it's basic. And so as we transition from excess excess acid, where it's acidic, so the solution is clear, to basic, we want that transition to happen right around the end point, the equivalence point. And so that's what we're looking for, is a sharp transition near the equivalence point. All right, now we're going to go through and actually do calculations to analyze these titrations. So we're not going to spend as much time here on the experiment itself and its utility in analytical chemistry. We're going to use it mainly to kind of practice our acid-base chemistry that we've been working on. Okay, so titration will have three parts: before the equivalence point, at the equivalence point, and after the equivalence point. So titrant is limiting, stoichiometric amounts, analyte is the limiting reagent. Okay. So the first thing we're going to do, the thing we're going to do for today, is the titration of a strong acid with a strong base. Then we don't need to worry about any equilibrium, we don't need any ice charts, so this will get us going. And then in subsequent lectures we'll go through different types of acid-base reactions. Okay, so strong acid, strong base. And so let's take the example of 25 mils of 0.1 molar HCl is going to be titrated with 0.1 molar NaOH. We know the reaction. This is, of course, one we've been using a lot, and you've seen it a lot in your book. So HCl, NaOH, NaCl plus water, 1-to-1 stoichiometry. And so let's just, before we even do any calculations, let's just try to think about what's going on as we deliver sodium hydroxide. Well, we put in a little bit, so we start dropping in sodium hydroxide. That will react immediately. This is a very fast reaction with the HCl, and the HCl will be limiting. So our pH will raise a little bit, but it will stay very low because we got a pretty strong acid solution here. In fact, it would be a pH of 1. And as we add sodium hydroxide, that will diminish the concentration of the acid, but it will still be acidic. Then we add just the right amount of sodium hydroxide. So in this case, we can just see it by eye. That's going to be when we hit 25 milliliters, because we happen to set this up so that we have the same concentration. So when we have added 25 mils, so we have 50 mils of total liquid in the container here, we add 25 mils of sodium hydroxide, then no limiting reagent, we have only water and salt in solution, so our pH should be 7, so neutral. And then we add just a little bit more. This is a pretty strong base, so this would be a pH of 13 if it was just itself. So we add just a little more base, that becomes excess, and we should shoot off to a very high pH. So let's go through and see how we calculate that. So let's start with before the equivalence point. So the first thing we have to do is figure out how many moles of HCl. And this is going to be set because we've put 25 mils as the analyte. So that's the same number of moles all the time. What's changing is the moles of sodium hydroxide. So we can quickly calculate, based on the concentration, that there are 0.0025 moles of HCl. Now we're going to add Y milliliters, or Y liters of sodium hydroxide. We're adding 0.1 molar solution, so 0.1 moles per liter, and we're adding Y moles. So we have added 0.1 times Y number of moles. So how many are remaining? So we're looking for the remaining, not how much have reacted, because we want, it's the remaining HCl that's going to determine the pH. So we're going to take our HCl minus our NaOH moles. And what we're doing here is really, in our heads, we're saying each one of these is going to react with, each 1 mole of this is going to react with 1 mole of that. Okay, so we're using the stoichiometry to figure out how many moles of HCl are left. Well, that many moles are now in how many mils, or how many liters? Well, not exactly 25 milliliters. We've added a little of this sodium hydroxide. We've added Y amount. So our denominator here is 25 mils, right? So 0.025 liters plus Y liters. And that's our H concentration. So we just take the negative log of this and we'll get the pH, right? So you can go ahead and practice by putting in, say 10 mils, then see what the pH would be. Okay, now we have to go to the equivalence point. So we've added. We've kind of by eye already determined that when we hit 25 mils of NaOH, we're going to be at the equivalence point. So let's consider at the equivalence point. For a strong acid, strong base reaction, this is a very easy calculation. We simply say we've reacted totally, there's no excess. We only have sodium chloride, which is not going to be either basic or acidic, and we have water, so we're going to have a pH of 7. So that's pretty easy right there. So here we get the pH all the way along up till the equivalence point. The equivalence point is 7. Then after the equivalence point, let's calculate the number of moles of sodium hydroxide. That's exactly as before, right? Because that's just what we've added in terms of volume. But now this will be the excess. The sodium hydroxide will be the excess. So, whoops, this should be a minus. So we have 0.1 times Y minus 0.0025 moles of sodium hydroxide is left. So just like before, our concentration is given by the total moles that are in excess divided by the total volume here. And that will give us then the OH concentration. So to get the pH, right, if we took the negative log of this, we'd have the POH. So we take 14 minus the negative log of this. Now, what I encourage you to do is calculate points along this addition. So let's make a graph here of pH versus milliliters of NaOH added. And I would suggest maybe go steps of 5 up until you get to 20 mils, and then maybe do steps of 1 up until you get to 24 mils, and then 0.1 or 0.25 until you get up to 25 mils, and then 0.25 until you get up to 26 mils, and then 1, and then 5 again. So really pepper the calculation right near here. And what you'll see is a very steep rise, which indicates that this would be a very good titration base reaction for doing a titration. So it's a good acid-base reaction for a titration. All right, so this is our first titration, strong acid, strong base. Now, as you might imagine, we want to do, say, a weak acid with a strong base, in which case we're going to need to do some equilibrium and ice charts, so we'll throw that on top of this. So before you move on to that, really feel comfortable with this, really understand the idea of a titration, and then you'll be ready to incorporate what we've been learning before about ice charts and equilibrium into a full-blown titration.